Okay, then let's start the fifth day. Today we have another very interesting lecture coming up from Felix Amtsberg. He's gonna talk about the automation technologies that exist already in industry and how they might be fundamentally different from what we're doing in research and where we want to get with the technologies that we're using in research. Before that, we have again 1 hour to run through your projects. Maybe with the experience from yesterday, we're gonna need probably a bit more time again. So I guess after the break, we're also gonna continue with the projects that we didn't manage to talk to yet. And with that, maybe what we could do is to start with well, should we shuffle the sequence, or we just no? Let's just start again with group 1, and then if one groups wants to present already in the first session, then just tell us. In the end, I think totally flexible. Okay, group 1, are you ready?
We can hear you. Are you ready now?
Hello, good morning to all my friends and all dear participants. Just I was trying to open my, yes, all the photos are uploaded. Okay. I will start just describing and explaining what I have done from yesterday. And after that, my dear teammate Jennifer Rose would explain the second project that he was trying to solve the problems about the isocurves of the angular sitting on the slab that he was trying to solve it and present it to us. Okay, so I think I can share my screen. Okay, do you have my screen right now?
Yeah.
Okay, first of all, I try to have some experiences from that BM layouts that dear Shai has an effort to tutor us yesterday, and I try to promote the previous. I'm sorry, just the photos are a little disorganized. I just tried to promote the code that I had from the day before yesterday, that I had some problems and difficulties for solving and getting the isocurves. And with solving it and getting the topos results, I try to just have some optimized center lines, and after that optimizing the dimensions of the modules that we can use for constructing and having the BIM layouts with their modules. And after that, I had the BIM layouts here, but they had some just errors or just collisions that I tried to check orally all of them for not having collision in some parts. So I tried to check the collision parts, or the parts or nodes that we may have a collision, and I solved them in some parts, and finally we received the final result of these beam layouts that we can see in the picture. And after that, I try to promote this idea and concept of these polygons that I had a code that it can generate these polygons with just some curvular angles. Um we can generate it from triangular just polygons to every how much edges that we can have and we want to have for our design process. And I just sketched a building. For example, we can have that we can have just some cylinder homes, and with combining them we can have just for example, I think we can say that it is a kind of metabolts. And with combining these polygons from skewer to the polygon, I don't know what is the name exactly, the polygon that it has 5 vertices, and to 6, we can have we can transfer from just uh, the places that they are crowded to the singular homes or cells. We can imagine that can build for 2 or 3 people and transfer it from polygons that they have some more edges, some more vertices and edges, because surely they can give us some more soft and fluid places for just some public places we can imagine for having in building. And as you see, we can have with combining these cells, we have in these buildings, we can supply cells for just every much of people that we can consider. For example, for 2 people in singular cells, or more than that in with combining these cells. And I'm sorry, and we can see just some other perspectives of these buildings. And we had a concept of these fluids that it can give us interesting curvular sketches and concepts that they are fluid, and they have somehow interesting perspectives. And after that, we try to have a modular and grid sketches and designs, as Hannah said yesterday, for having for uh, it, a sketch or a design that we can potentially develop it from every edge or every side we want. And with the and we can have slabs that they are triangular, and with combining them we can have skewer slabs and spans that they are more compatible with the lifestyles that we have in our own homes and in our own buildings. And with combining it in different multi-story buildings, We can have different functions in combining them in different levels and having them in multi-story. It's just this. My presentation and my explain about sketches and uh, designs have been finished, and I hope my dear teammate Rose is ready for his presentation. Thank you, everyone, for hearing us.
Is the screen visible?
Yep.
Okay. So this is what we had experimented yesterday with slabs that were flat but not along the XY plane.
Mhm.
And yesterday you had mentioned, you had suggested that we try a more flexible layout in terms of stacking vertically or horizontally, like how the same idea would work on a larger system.
Mhm.
So this was a step, a process of how we try to convert it in a larger system. And one thing that we had faced was when we try to stack vertically, we can again not go for a conventional packed stacking. That is, since the slabs are angular, we cannot continue the same way for, say, the roof slab of the ground level could not become the ground floor or say the floor slab for the first level. Uh, uh, I mean, was I clear? I think I confused a little bit. Can you hear me?
Yep.
Yes, we can hear
Okay.
you.
So the problem was we couldn't use the ground floor's roof slab as the floor slab for the next level. So when we were trying to stack it, we thought that instead of having a stacking each floor exactly one above the other, we could have some breathable spaces in between so that it would allow us to go on a larger system which is vertical. So the way we or the process that we had gone or undergone for that was we just took a simple boundary of a circle and populated with some points, came up with a Delaunay mesh, and then created a NURBS curve from the mesh or a surface so that it could mimic the original idea we have. And further, this is for the ground level. But since we have the constraint of not being able to stack one above the other, what we did was we defined a few areas, say for a few circles, which could probably be the spaces that the designer has in mind for his next level, and create some points only at that level and create another meshing for the roof. So this is the idea that we had, that instead of stacking each floor exactly the same at ground and first level, for the ground floor, we would define the points based on the spaces. And when it comes to first floor, we wouldn't follow the same layout, but a different one, again, depending on the criteria of the designer. So we tried it. So this was the plan that we had for each floor. And these are some of the interior views that we took for it. And this is the isometric for each floor. So ground, first, and second. But there's still some work that needs to be done, like say for example the column optimization. Since each floor is differing, like the layout differs, we need to make sure that or optimize it in a way that there aren't too many unnecessary columns, but still tries to satisfy the need for each slab. So that is one thing that we are yet to optimize. And one more issue we faced was when we tried to take this onto the net simulation definition that was given. We were not able to get the solution for it. As Shai had yesterday mentioned, that there would possibly be an error because it was not, the definition was necessarily not meant to be tested on a angular slab. So we had this issue of the model component becoming red in color when we give the inputs, and it says an error that says there is no context bound to the current thread. So I'm not sure how to rectify this either.
Can you show the input geometry?
This mainly it's because the input geometry have no intersection or don't have enough intersection. So there's no element in the columns or no elements for the loading.
Okay. The two elements I have given, the boundary domain and the supports, they are actually not intersecting. They're just touching each other. So maybe I will try intersecting both of it and do it once again.
In this view, I think the column may can you turn on? Maybe the column is need to be more. The radius maybe should be larger. So just to have enough intersection to include several elements as support.
Okay. Okay. So
I'm sorry interrupting my teammates. Last night we tried to even extrude the columns overpassing the slab and just having surely an intersection with this angular slab. But finally, again, we had this error as the same that we had when our columns extrusions was exactly intersecting until the slab. Thank
you. And also, I would say that the thickness of the slab also need to be larger. So I think I explained once that when you divide it, when you set the resolution, it's a resolution in x direction. So the d direction will be divided with the same element size, but not with the same resolution. So if you have if you plate is very thin, so there may be no element at all in the z direction.
Okay. So I will try that out too. So that's it with what we had. I mean, this is the progress that we had come up from yesterday, and we were not sure about which route to take and proceed further with the project assignment, because although we would want to try with angular slabs, we were not sure whether we are going in the right direction. So we have two options, which so that we could get your comments on it, and we could, proceed further on which route would be the better option to continue with the project.
Yeah. First of all, that's really cool work that you're doing. I think pretty interesting. So in the end, if I understood correctly, there's kind of three directions that you're kind of exploring, right? There's, if I may call this the cobblestone approach, right, where you have this kind of elliptical shapes touching each other tangentially, right? Be it actually, for now, I don't see too much of a difference whether that's whether those are slightly inclined or horizontal. Then you have the hexagon ring approach, right? And then a very, I would say, very stringent grid-based approach. Where the grid one, I didn't really understand how it's breaking free from the grid, right? So I think that's maybe not the most interesting. And then the ring one, I think that one was really, Alireza, that one was really high developed already. I think already managed to put the beams underneath, right? So that's pretty cool. What I'm not sure is how you guys are gonna put yourself out there, ideally in terms of like really developing a unique project. I'm not sure if you missed that, but I remember, I think group 10 also had a very similar circular structure, right? Based on that, maybe it's more interesting from a global perspective, right? From the whole, taking into account all the participants of the workshop and what kind of directions they're going, and to kind of maximizing the diversification. Maybe it's good to go further with this kind of cobblestone approach. But in the end, I think it's up to you what you want to do. I think the approach, Jennifer, that you showed, I guess based on the problems that you had in the simulation, is still a bit diagrammatic, right? I'm also not really sure if you should introduce like a secondary hierarchy of slabs, right? If you go to the last image, where you have your cobblestones, or maybe we find a different way for the different name for that, but I'll just call them cobblestones for now. And then you have this kind of continuous slab, right, where you say, okay, this would then be the surface of where the inhabitants, I guess, would kind of move around. And I think that's a bit unfortunate, right? Wouldn't it be way more interesting to have this kind of discrete arrangement of islands be also the environment where the inhabitant kind of walks through and explores? I guess of course there is some more detail to add, I guess, to see how this could be actually inhabited, right? But I think if you need to introduce a secondary hierarchy of this kind of more continuous slab, then I would rather either keep it a single story thing, right? Or maybe also just think about how to have the cobblestones merge a bit more. What do you think about it?
That we had in mind was to show some more flexibility than just a single story pavilion kind of structure, which is.
Sorry, you're very silent. I can't really hear you so well.
How about now? Is it audible?
No, it's way better.
Okay. So we felt that this layout was quite say defined, where the flexibility is not much depicted. So which is why we wanted to try with different levels. But as you said, the continuous floor slab doesn't really go well with the idea. So we need to rework on that part. And I think maybe we will stick to just a single level for the development.
Yeah, I guess I would be interested to see some kind of path going over this kind of cobbles, right? If you stay on this screen, then I could imagine that there is a certain route that people could take, right, around here, and I think that would be really. I mean, maybe it's not really pragmatic in terms of like what this would be functionally, right? But as let's say a spatial experience for the visitors of your structure, maybe that's really interesting, right? Just to just have this kind of landscape to walk through, and if you will, then I would even say that this maybe we call the better name to call this kind of patches is like maybe even leaves, right? Where you say like, okay, the overall experience of your structure is as if you walk through a kind of through a foresty three-dimensional environment, right? Where like through the I guess the advantage of this kind of structure would be that you can get light, even if it's only indirect, but you would get light everywhere, right? So even if you have 3 floors, if all of your floors are comprised of this kind of segmented plates that only touch themselves tangentially, you will still have quite good light conditions on the bottom, right? So this could be really like a three-dimensional environment where all the floors are pretty nicely lit, maybe, right? I think that would be pretty exciting.
Yeah.
Actually, actually, this project reminded me of the work of Frank Lloyd Wright. There's a office with a roof of circles and columns. Can I share my screen so you can see?
I will stop sharing.
Can you see this example?
Yes.
Yeah, I think it's although this is like standard circles and columns, but I think it shares the same spirit with your proposal. And I also agree with Jakob that it's really a little weird to see the continuous slide as another language in this design. And if you make it multi-story, I think it's really hard how to deal with the relationship. If you have a roof as the patterns, and then you have another slab upon over the roof, that's a little. I can imagine how we'll deal with that. So my recommendation will also be you can stick to one given language and pretty much like that.
Okay. Yeah. So we will work on that and get back to you with some more progress tomorrow. Also with more networks and the beam layouts. I think we will be able to do that by tomorrow. I think that would be very helpful.
Thank you very much.
Yeah, hello, can you guys hear me?
Yes.
It's George and Chris here, and I'll share my screen. There we go.
Morning all.
Can you guys see the screen?
Yes.
Okay, so I'll start where we left it off, and looking at the single cell organism, we rationalized it into a simple shape, and this is kind of what we studied last time. We're still interested in looking into this modular typology and how it could grow, and we rationalized the shape from what we had. And we're more interested in the structural varieties you could achieve, even if the slab structure is not as organic. We are more interested in, on the singular level, how you could have more structural variety, but also as a system, how these units could start connecting and what type of geometries and structural systems they would create between them. So this could grow in any direction, which we found was interesting. And you could start, what we found interesting is how they could start stacking, either as a tower or horizontally. So what we chose to look at in particular was keeping a constant column location, but how that would change the structural system on every level. So if you start looking at the stack, you start getting the intersecting regions, which can be used to define or populate the column location. So there's always a relationship from one level to another. Now the step forward, which maybe is for another time, is to start looking at staggering the columns. But we wanted to start with this and develop it. So I'll just show some results that we got on the single level. So we tried cutting the isocurves at different heights to get as much as many connected lines to run as possible, and we got an interesting first result, which worked. There are collisions. I didn't turn that on because it was starting to go a bit crazy. But I think as a first go with 3 columns in an irregular arrangement, we found it was quite successful. So this was the first test. And then we did a quick study on what that would mean when we would connect 2 together. So that's the analysis. That's the single. Here's the double. Now we didn't add the beam layouts, but we did do both successful and unsuccessful studies on what the relationship between 2 modules would be. And I think you start getting some pretty crazy and organic roof structures within the constraint of the module, which we found was really interesting. And then maybe I'll leave it to Chris to kind of explain how it grew into a system and how maybe some structural constraints that were a bit of an interesting issue. So this is how it would grow, and spatially it could grow vertically and horizontally. Chris?
Yes, I think the system itself, what we chose here is indeed keep the columns continuous, as in that in that case, a different column position, if they would not be continuous, they would definitely influence the mesh pattern. And the pattern generated, because it will be strongly influenced by point forces. We hope here that if we keep the columns continuous, that we can basically reuse our analysis of the first floor and stack it on the third floor, and then just by copy pasting the elements. I think that's more our practical approach for this week. because with unlimited time, you can of course simulate every unique configuration and every floor. And as George already said, you could easily continue this system and let it grow into a tower, or continue it horizontally to let it grow in that direction. So it provides a kind of system and opportunity to actually start to make a building. In addition, I can tell a bit about the other side. What we have done, we have did some more unsuccessful studies. What if we would change the material towards timber? As in originally, it's simulating with a Young's modulus corresponding to steel. So I thought, let's move it all to timber, and the results were, let's say, disappointing. So there is some instability there, which probably caused by that just the height of all the elements is just too low, which will cause an unstable model. Because for timber, you probably need instead of a slab of 300, which we simulated now, would probably have to simulate it with 5, 6, 7, 800 millimeters. Yeah, still curious if we can get it to work, but for now it's really something that I see. Okay, let's just make it out of steel or something. Towards the slab pattern, I was thinking there are actually in a beam you always have a compression side and a tensile side, which the two sides will swap above the supports or in the middle of the span. And I think the slat pattern isn't to be it's really structurally efficient will be different for the compression side as for the tension side. Where in compression you basically just want two ends of a slat to just push against each other at the contact surface to transfer the loads directly between slats. While for tension, you definitely want to transfer that on the parallel surface through adhesion and the glue, instead of on the direct surface to get a better bond. So it's the kind of direction what we see, which may be interesting to explore for the generation of the timber itself. But it will require that we will start to get to know where's the tension side, where's the compression side for each beam. And I think that's it.
Thank you.
Okay. Pretty cool. So I'm maybe let's start with with the general layout, right? And I find it super interesting how you're stacking up this kind of shifted layers, right? Shifted and rotated patterns on top of each other, right? And what I wanted to understand is the column positions at the current moment are designed in a way so that each column is always going is kind of over is holding both the second and the first layer, right?
Yeah, that's correct.
Yeah. But it causes a completely different structural configuration on every level.
Yeah. And how did you design these columns? Like you basically had a look on how they overlap, and then you place them in the
yeah. So
spots,
the parameter is the intersecting region. We tried several different layouts, but we found by rotating it by 45 degrees, we would have a wider structural possibility. And so it's really within this wider region that we can begin playing. And there's also the constraint of 3 columns per module. So it's 3 for the bottom one and always 3 for the top one.
Yeah. What I would think would be interesting to see. Maybe that's just a little fetish of mine. If you don't see that relevant, then just don't do it, right? But I would be interested to understand this kind of positions of the columns a bit more on a let's say more systematic side, right? Is it so? Asking the question: is it possible to continue this pattern, right, of this kind of four-armed panels or cells, as you call them, and have them supported by 3 columns, right? I think that sounds like a very fun schematic exercise, right? So how do you need to overlay your layers, right? So that you can always get like a stable constellation for each of your cells, maybe with the question that you ask, like with the minimum amount of columns, right? I guess naturally everyone would ask, like, okay, you have 4 armed cells, why do you use 3 columns, right?
I think that from a structural engineering perspective, we will just, in this case, say we want a bigger cantilever so we get a nicer pattern. Normally I would never say that, but I think now it gives you get better lines of the now we are having the bigger cantilevers.
Yeah. So I guess you could just say you wanted to. So 3 columns, I guess, are the minimum to achieve like a stable support, right? And then maybe the question is, in general, like if you overlay those different patterns, right, then how can you achieve like a stable support of each of those cells, right? While then maybe the question of whether this kind of constellation of columns for each of the cells is the same in each case is less important, right? As you can kind of adapt to it. Right? So yeah, I think that's interesting. But I guess as it's so specific, I would guess that it wouldn't hurt to explain. I don't know, to give like a 20 or 30 seconds diagrammatic explanation of what is really the kind of spatial strategy that you developed here, right? In terms of like, okay, how do we organize our space, right? And yeah, I guess I would just try it, and then if you figure out that in the end it's really just a matter of trying to get interesting patterns, then maybe that's also fine. Yeah, but it also seems that the tools are working for you guys. I guess doing topology optimization for wood as an anisotropic material is like beyond the scope of the workshop, probably.
Yeah,
but I'm not even sure if anyone achieved that already. You know, someone?
Yeah, well, I think there's when you see just modifying towards timber properties is also something which I think we will just ignore, as in it will just make the models unstable.
Yeah. I guess one could make a proposition that we can, as we are able to arrange the fibers in the way that we want, right? We would then almost achieve an isotropic quality, maybe. But I guess still the stiffness and yeah, the values would still be very much lower. Well, okay, you could argue that it's hardwood and stuff, but okay, I think that's really an interesting exploration, and maybe we should go on to the next one. Otherwise, we're gonna be here until long overtime. Any other questions from your side?
No.
I think we're clear. Yeah, we have more ideas on how it can grow and change.
Cool.
Thank you.
Cool. Thank you.
Hello, everyone.
Hello.
It's Ahmed on the spot. Okay, can you see my screen?
Yes.
I'm not sure which screen I'm showing. Okay. So we were looking at the beams articulation yesterday, and we had some goals and strategies to guide our way. So the first goal is the reconfigurability of the beams itself. I mean, in the life cycle of the project itself. And we were looking at better beam dimensioning, the sizes and the depths of the beams, and also material efficiency. And we are looking how to showcase the Robo platform in a more advanced way. So, and we had some strategies how to, so we wanted to reduce the glue. And as Chris said a few minutes ago, load to see how load would transfer. And the last thing, to utilize the mill and sew from the platform itself. So we started with the beam function to see how it works. So basically the slab will take the vertical load and do kind of 2D load distribution, and then it became vertical. I mean, like the line, the beams will receive a vertical line load, and then transfer the load horizontally to the beams, to the columns, which will transfer it down there. So basically, the main stress would be horizontal stress. So and we also noticed, as Chris just said, the in the current configuration, it's more into tangential shear load transfer. So the part which is active currently would be the surface part, which already has a glue or an adhesive material, and there will be also partially structurally active both sides in the timber, opposed to the normal beam configuration when it receives normal forces from the sides. In this case, I think at any point, I'm not a structural engineer myself, but at any point it should have half of the compression load and half working as a tension. And we think it utilizes the section, the material section in a better way. So we just looking at the classic dovetail connection, since it can take both compression and tension forces. So the system, what we're proposing for beam articulation, that we will use the standard wood struts, which we call it Mac beams with a dovetail, and there will be cut pieces like those, the yellow or orange color. Those would be cut in situ and maybe laminated in situ, or it doesn't really matter, but I think it will reshape and fill the spaces in the curve when you divide it to standard pieces. And basically, the use of those yellow would help to stabilize the beam itself and also carry the load horizontally. So we were looking also at the assembly sequence, since it's this is the slab, but it's upside down. It's like a robot is building on top of the slab right now, and then it's gonna be flipped. So we rearrange the macro beams and then just nail them at the 1/3, and then just fix them with the lock pieces. And the next stage would be just alternate the second layer on top of it. we think that the slanted dovetail connection would actually minimize glue usage. It would be partially in the connection pieces or lock pieces, or maybe laminating some parts in situ. I think it's gonna be it's gonna have better load transfer and smaller dimensioning, and it would showcase the Robo platform beyond the glue and deposition of the material. I'm not sure how we're gonna use the saw exactly to cut those angles, but let's see if looming is gonna be around. Just go back to the grasshopper. We tried also to script this somehow. Yeah, we just managed to make only small 3 prototypes of the system, which the first part was the struts of the macro beam and the connection solve and like the node. So what was a bit difficult to do is to divide the lines or the curves into standard pieces plus the nodes. So I think it would take a bit more time to do this. Yeah, and we've done also some special configurations. I think Misbah can take it over from here.
Yes,
yes.
Yeah,
okay. I'll just stop sharing.
Okay, so as from a conversation yesterday, we generated slabs using the metaball strategy, and we wanted to kind of differentiate the conditions on the multiple layers. We're thinking of having multiple roof layers. So on the most bottom floor, like we're thinking of having a regularized column structure, but on the next layer, we wanted to break free from having columns in the space and make it more freestanding. So the roof on the second layer would be divided into smaller chunks. So like 2 conditions we thought was of just having columns at the boundaries, so the space is still free while it also overhangs, and just having a singular column at the center. And we tried the grasshopper definition in it, and the load transfer works fine. And we optimized the surface as well. And these are the center lines generated. Nice ones. Structural diagram. And this is what we achieved using yesterday's definition. We have 8 layers of timber over here in this particular floor slab. And on the top ones, we reduce the number of timber layers, like we have a maximum of 5. And after this definition, we further optimize just the floor slab to cut away from the overhanging spaces, just to make the slab more thinner. So we just optimize it after the whole definition was done. These are just a few views of that. And yeah, that's all.
Okay. Cool. If you don't mind, I come from the back, right? So I'll first, or we can first discuss the spatial studies and then the joining. It's so this is super cool. It seems though that the topology optimization, I think there's some curious things happening there. I think it was working, or it seems somewhat logical for the top plate, but for the bottom ones you have two columns that that have no beams running to them, right? That's usually a sign of something being running in the background, or within the process, something being left out, right? So maybe those columns didn't really get included in the within the processing, right? So maybe for this it's also best, maybe we don't discuss it now, but you after the session or during the break we do a small breakout and see if we can fix your definition and see if something's
when I optimize the slab though, like everything works, like the columns are taken into account.
Okay, but then how? Actually, also in this picture, you see that there is beams going to all of the columns, right?
Yeah.
So then maybe the problem is at the generation of the center lines.
Okay.
Maybe the optimization process is not fully run. Or I think this mesh is definitely not what we want to use to generate the lines. You can see, okay, draw. In the right part, there's the whole area that was extruded out. So if you get, so this part, you can see you cannot see any differentiate area in this part. So if you want to generate some center lines, it obviously it won't have any relationship to this column.
Okay.
I think it needs to be optimized more, or with more resolution.
Okay, I'll try that as well.
Okay, then to the joints. I think that's really an interesting study. I would definitely think it's worthwhile to go a bit into deep with that also. It would entail that you might come up with a bit of a different building system as we're currently building in Shanghai, right? But the same platform also has this kind of spindle. So there is a machining tool on the platform, right? So you could show probably the simulation of how you would cut those dovetails, right? And how the robotic fabrication part would change to enable the joining of the slats that are basically in one layer, right? So I guess I would still use the glue to glue layer on top of layer, right? But then if you also connect them in the same layer, I think that's a really cool contribution, and definitely also worthwhile to maybe investigate further. Right? What do you think, Chahul?
Yeah, I really appreciate the thinking and the research for the different layout and the different methods. And I think the platform also provides several different fabrication methods, like you can drill holes. I think we actually have a drill on it and have a circular saw on it, and also a spindle, and also I think you can take use of that. But just the worry. I'm a little worrying about the how after you get all the joints and how to place how to connect all the joints with a very concise way. I think if you want to have this kind of joint to work, it needs some very very tense contact between the two parts that will join together. So in traditional carpentry in China, if we want to use these kind of joints and without any nails or something else, sometimes we need to use hammers or something else to like post them together, like they can work very well. So in this case, I'm not sure if we can just post them together and they works that well as actually I'm not sure about this.
I guess actually it's, I mean, in this case, when we lay them down in a straight condition, we could have a bit of tolerance, let's say 1 or even 2 millimeters, because once they are flipped around, then and start having having loads, they will take this kind of sagging position, and in this position, they will just press and tension each other together, and they will hold together. It's kind of the actual locking and the actual fixation would be only when the structure is active. There is no problem if they are a bit loose here. I mean, like, of course, there is a tolerance has to be calculated, and I think also it would be precision issue with localization and positioning of the material itself. Yeah, this is something I think we would like to experiment with and see if there was any solutions. And I think there is no harm to just try different configurations, how to mill what size of tolerance. Does it work when we flip it without glue, or does it need to be glued? But what we were looking actually from the beginning is to cascade down the freedom of the design to the end user. So that means at any point of time, the beams could get wider or deeper, or even, I mean, kind of reconfigured and stacked on top of each other. And also what we had in mind at the beginning, I mean, the shape of the beam, it's not going to be one layer. This is only the first layer. We were just more looking into the articulation, which Jakob started with at the beginning, this kind of half pipe shape, which tapers down till the end. So that's what we were just having in mind during this, and yeah, that's it. So I think it would be more experimental way of finding the right configuration and test it.
Okay.
Yeah.
With that, we should continue with the expert guest lecture, and then we'll continue the project reflections after the break. Thank you so much, Mahmoud and Misbah. And with that, let's give it to Felix Morning,
everybody.
Felix joined ICD now pretty exactly a year ago, I think.
Yeah, exactly, on the day.
On the day even. Wow. Okay.
Yeah, if you think
So
about
actually it's an anniversary lecture.
Yeah.
Felix received a PhD from Graz University and was working in MIT and in SUTD in Singapore, right?
Correct.
As a postdoc, and is now also a postdoc in ICT, and also working in the excellence cluster with Louis, Hannah, and me. So yeah, I'm just gonna give it away to you. If I miss something, just maybe.
Okay, yeah. First, no, thank you for the introduction. No worries about that. Most important question is, can you hear me so far?
Yes.
Can you hear me?
Yes.
Good.
Yes.
Okay, good. That's important. I'm not too far away or anything like that. So let's start with just sharing my screen. And if you can see that, also tell me that you can. Okay, I see. I would also saw it already. Okay, excellent. So I mean, I have you somehow a little bit like in my way. I'm just going to push it on the side. Okay, so I think it's the day 5 of this workshop, if I counted it correctly. Seen interesting work. Also, I followed my colleagues. You see, you get the total package of ICD timber experts somehow, or that what we try to become, and where we do and do a lot of research and investigate current technologies. And for example, me specifically, I'm focusing on the state-of-the-art automation technologies in the prefabrication in the timber industry and for the fabrication of wood architecture. And obviously, like, so this is where we see a little bit of a glimpse today. I will like run through like having like a quick introduction what we're talking about, then talking about the companies, key figures in terms of using these elements, but then also like talking a little bit about the providers to the machine technology and so on. Try to like show a little bit like what are trends, and then we maybe can like discuss quickly about how we conclude with what we know, what's happening in industry, what's happening in academia. So we now for this workshop represent like the part of academia, but usually like this is why our like perception of digital fabrication usually looks a little bit like that, what we see on the left. So you see like on the bottom, the mobile timber fabrication platform that you somehow are going to work with, even if it's unfortunately a little bit more remote as you expected it to be. But also like the prefabrication platform DIM that I'm sure Jakob introduced in one of his previous lectures. What is like this container-based 2 industrial robots collaborative platform that was used to fabricate the Buga wood pavilion. So what if you look at industry, we won't see that much of robots or versatile machines. They're going to be versatile and they're going to be generic, but they're going to look completely different. So like these two of the most important examples, I am also like going to show them how they work in fabrication are like a multifunction bridge and a joiner machine. These are really, really essential machines. And if you ask about, or if you talk to people in industry, that's much more what they're going to think automation in timber prefabrication looks like. So also like a quick like recap of what we're going to talk about, because there are some like, you could say like 4 categories of what we could talk about. We could talk about like 1 family houses with frames. We could talk about, about this one. This is a mistake obviously in this this module based building. That's obviously not Brook Commons. You've seen it a lot. That's this high rise that we see there in the middle. So this would be more timber module based and buildings. And then we have, for example, like here on the right, 9 Bridges, the country club by Shigeru Ban architect that was like realized in collaboration with design and production, and Bluma Lehmann on the side of fabrication. So this one on the right, as intriguing as it is, we are not more talking about like housing and not about these special structures, because obviously they request much more of an individualized prefabrication system. And if we think about housing, we see a lot of more like a trend in the direction, or like not even a trend, it always has been like the idea that standardization is something that helps you to build effectively and efficiently. So, and in the end, it also means like, if we then look back, like what are the, you've seen it in the section, for example, from Louis already, what are like timber elements, like the basic elements we are talking about, some sort of like plate elements, as you can see on the left, or like a lot of stick elements. And if you think about it, like every timber structure somehow can be like broken down, that this is done by stick and plate elements. You know? So what is like interesting also like to understand quickly, or like, and also that they, if we looked at plate systems and for example in this case usually CLT based systems, like an engineered planar timber element is like one element that you see on the right. It is mainly produced by with subtractive processes, so it's going to be placed on a CNC bridge and it's going to be machined and that's going to be installed. We're going to look in that a little deeper in a second, and we will have some sort of like lightweight panel-based systems where you see like where you see like the stick elements, where you have linear members that are somehow prefabricated and arranged and assembled, and also like machined in additive and subtractive fabrication processes, and they're going to be assembled on site to become like this kind of building site. So we see we have some sort of like, you can, I mean, obviously there's several ways how you can like distinct and separate building system from each other. But one I think makes a lot of sense to see that we have like some sort of solid systems and lightweight systems. So, and usually like no matter what, like this is going to be, we're not going to talk too much about, again, we're talking about the offsite prefabrication of these elements. So, but no matter what kind of element you're going to have, this is going to be more or less like the end product that's going to be brought on site in like sizes that can be transported by a truck, and then they're going to be assembled on site and going to be result in more or less nice housing or building systems. So what there obviously matters somehow is like the level of prefabrication. So, and if we look at like these linear elements, as we see on the left, we will have like a different way of level of prefabrication. We have a different level of flexibility. For example, if you look like prefabricated elements that then are brought on site, as is usually the case for like either panel construction elements or solid timber elements, you will have like a higher on-site fabrication time that's going to decrease if you take room modules, but you also see some sort of like the level of flexibility seems also decrease a little bit, yeah. But the level of prefabrication that you do offsite is increasing as well. So that's something like to keep in mind if you think about what you want to plan in terms of setting up a fabrication factory, that you want to have like a good balance of on-site and off-site fabrication. And we somehow think that also might switch, or depending on what kind of adaptability of the system you want, you might want to change this balance between for the level of prefabrication. So obviously, like the transportation constraints matter. Like by law in any country, we will have like a certain type of container or system that you can still bring on site without that you need some kind of special permit to go through the streets and to bring these elements on site. And this is also like that's a major influencing factor for what's the size of the elements that you prefabricate. You know? And usually, as you can see, like this will also be more or less like the max what these modules that almost look like containers that you place on standard trucks. They look like that almost. How they are like, yeah, the dimension of them are going to be fixed by that, and what you can transport. So this is a little bit like so the basic principles that we always have to consider. Like there are several others, but to point out just a few. Before like looking into companies, we're looking into three types of companies. Like on the left, how they are like more like these are like the builders, like the construction companies, and we have like two types that have been mentioned already. We have like what we call product-oriented companies and project-oriented companies. We'll like show a little bit later also what that means. And then also we have like the providers of the machinery that have some sort of influence, obviously, how these companies produce, because they obviously provide the technology that enables these companies to work and to produce and to prefabricate the elements that they want to ship on site. So going like before we do that and go to the companies, there's also just one side stream that we should make, or a side step that we should make is we've been seeing like if we have like stick elements, we actually like can take the raw timber, but also like there's a big stream of engineered timber elements, no? And for example, like a lot of CLT manufacturing is happening. And so we had a little bit like look into the companies that were working with that, and also like tried to understand or had a little bit and look like how do they actually produce these elements that then are going to be like 30 meter 50 by, or here 12 meter, you can see it here on the left, for example, like this is a Japanese company that has been a CLT manufacturer that has been installed by Ledinek, and where they installed like this machine setup that somehow enables them to take all these small elements and plane them, cut them, join them, and so on to fabricate these CLT components. They can be up to 12 meters long, up to 3 meter 0.5 high, and up to 36 centimeters thick. So roughly, these are going to be the dimensions CLT is available. Yeah, what is like somehow like run quickly through, we see that there's going to be like from the sawmill that you're going to receive like all these linear components. So also the plate components start with linear components, and there are like a lot of fabrication sequences that are actually run through these CLT plates then actually like appear. So we have like material handling there's going to be a measuring of the dimensions and the quality and the humidity and so on. This is going to result in a sorting strategy, and then these elements are going to be machined again, like they're going to be planed on dimension, they're going to be cut on length, they're going to have finger joints for like that you can achieve for all these elements, like these different lengths, or like for example like up to 12 meter lengths, or depending on the CLT manufacturer what kind of maximum length you need, and 3 meter or 5 like in width. And for and then like once they are done, so like for example like this is after the machines are like planed, they receive all these finger joints, then they're going to be oriented, glue is applied, and then they are like pressed and that way laminated, and that you achieve like these long elements. They're going to be cut again, going to be placed side by side, and in like X and Y direction oriented. Glue is going to be applied, they're going to be pressed, and then you have a CLT plate. And this is essential, like then you have like a few subtractive fabrication processes, like the standard company, like for many companies that have worked with them. For example, the company Hundegger, they are like one of the leaders in the market in terms of joinery and CNC machining of timber, and also like CLT, naturally like elements. And so they will have like a lot of machining tools that you can see here that allow us to do like many variations of subtractive processes, and that way machine like coming from a standard CLT that's rectangular to like a more individual piece that then can be already like taken on site and be assembled. So for like a quick like introduction into CLT manufacturing, before we then go like to the first company we're going to have an in-depth look in, that's a one family housing provider in Germany. They are one of like the most advanced in terms of technology in Germany and Europe. And they installed like a couple of years ago like a new manufacturing center and a new automated machine. So the company itself like has the idea they want to produce like 820 houses a year. They have like 170 workers. They work in 2 shifts. And they installed like in 2015 this new machine we're going to have a look at. and they have like a production line to produce like these kind, as you can see, like these raw timber frame elements for like a length between 10 and 12 meter long wall panels. They can be up to 3 meter high, can weigh like 170 kilograms per meter, and can have like specific window opening size. So it can have between 60 and centimeters and 5 meter 80. And they try to achieve, and that's like also really important, to produce like an internal wall in 20 minutes. They're at the moment more like at 25, and external wall, because you need like additional insulation, and windows can be part of external walls. That's not like likely for internal walls. That almost doubles the fabrication time to 45 minutes. So this is what they built their fabrication setup for, like an efficient production line for the manufacturing of these wall elements. They are not focusing on CLT, they are focusing on panel-based production. So this is like a picture, like they used to choose like this company Homag Weinmann, that's like a German machinery provider that installed them like this whole machine setup, and they use it as follows. Like this is also just like how it looks, like the digital twin of the system when it was planned, and this is how it looks now it is installed in science. But they actually look quite similar. So what they actually will do is, like, since they do not have like CLT plate but beam elements, like the first thing they will do when the beam elements are brought there, they're going to machine them. Yeah? So they're going to have a subtractive fabrication process for these frame elements. So they see a milling, they see a circular saw blade that's cutting these elements. And then once they have been machined like this, they're going to be brought like to this assembly station, this framing station. So on there you see, for example, the top and the bottom part is going to be placed on both sides, and then the robot like place all these vertical components. They're going to be fixed, and then they're going to be nailed with long nails. So this is like the first like fully automated, almost, I mean, this is like just like the guy giving it an extra hand in terms like something is not necessarily working, but in general, like it's a completely fully automated process that's done over there. So we see like an extremely high level of automation when we start the fabrication. So, and this is like how these elements then look when they are actually like in 2D, and there you see them like on the fabrication on the belt, where they're like one after another are like placed after they're assembled. And you see like that they have like two ways, or like so like if you have like, this would be like the standard length of a 12 meter frame, so everything looks quite simple. But then if you like more on the roof structures, you might have like subframes that are shorter and so on. And so they still are going to produce them like in this 12 meter length roughly, and then just going to have like a nesting tool that's going to make these three elements in the prefabrication step number one, the assembly as one, and then they have like these additional like like cuts, where they then just take a sable saw and by hand cut them off and separate these elements from 1 into 3. And then they're going, and then we see like this is like where like the first step of like a human labor also starts to interact. So you may have like this guy who places some for wiring for HVACs and electricity and so on. And this is actually something that's happening like one step later after the multi-bridge like plays this cover layer. So I just wanted to show like that there is some manual labor involved in like specific fabrication steps. So this is like one of the first. You see there's no cover plate down here. Here's like a cover plate underneath, and let's have a look quickly like how this cover plate is laid. So what we actually need to do that is like two things. Like one is a gripper, and the second thing is a multifunction bridge. So what is going to happen is that this also like this automated process are going to take like these gypsum plaster plates, bring them on a 3-axis CNC machine that like cuts these cover plates and then places them on top of these elements. And then this multifunction bridge, what is like this portal with like several versatile end effectors, they're suitable for drilling, sawing, milling, marking, screwing, nailing, and even like placing insulation in some cases. Not in this fabrication setup, but in general they can do that. then they're going to nail and cut these elements and fix the cover plates on the top side. Here we see like a little bit like of the different sequences, what is can be done, like not in the setup, but what like Omar Weimann provides. So here we can see a play like a circular saw that's cutting off like something that's extending the frame. Here we see like a placement of several screws. Here we see like how it would look like if you would blast in insulation, like a cellulose material automatically in this wall, and that way have like an insulation material. And here's like a close up, like how you could for like electric socket somehow drill some holes to do that. And once all these things are done for one side, a second step happens, or like another step happens, what means you have to flip this element. So it's going to be brought over here, and then there's this called butterfly table that then like lifts this element like from that side. This one they are like closing like a scissor and handing over like the cover plate side inside to the outside side, and then the step can be repeated and the outside plate can be placed. Once this step is done, like both sides are covered, like the previously horizontal fabrication sequence that had like a huge level or a high level of automation is going to like rotate by 90 degrees. So they're going to place upright, that you can place the windows that are going to be done, that you can apply plaster, that you can do additional works and so on. So the finishing at the moment still is like almost completely manual. There's no automation. I mean, there's something like this system like still this gantry system like still like moves the material, but in general like it is all human labor that's actually executing these fabrication steps. So we looked at it and try like to see actually like where we have human labor and where what are they actually doing. So what this diagram actually shows the production workflow and level of automation for the offsite fabrication of these wall panels based on what we've seen in this one family house provider being Zenka. So we have seen that here was like this framing station that's done by the robot where everything is like completely automated. Just the only thing that's done by human is actually like loading the material sometimes, so like even like in an indirect way. And the same thing happens like for the panel saw that cuts the cover plates. And then like this frame goes on like to this framing station with the multifunction bridge. And then the cover plates are placed on that, and all these additional steps I was talking about, like the stud placement and so on, are going to be done partially by human labor, partially by machines. And then the element is flipped again with this butterfly table as I was showing. Installation is placed, and the element again is like, it's placed like on the gantry system, lift upright, and the finishing process, like after the butterfly table flipped it and the second cover layer was placed, all these additional final steps are done to finish the wall. So I hope that gives you like a rough estimation, like how a fabrication of these lightweight panel-based wall elements looks like. And what is also important to understand, like this is a company that is like a product-based company, what means they provide a housing type that you can choose somehow, and then they're going to prefabricate it for you. We will now have like a look at the more project-based company. Before that, quick recap. I forgot that I wanted to say that. There, in general, like you see a high like level of automation in the prefabrication. What, for example, if you have like jam walls, so walls that do not have like a height that fits the automated fabrication process, or if you have walls that include downstand beams because they have, for example, like a huge window in the door over there, these then are actually done completely manually. So you see the assembly sequence by this one on the right, or like a little bit more in the background is the fully automated one. This one in front is a completely manual one that does actually essentially completely the same. So we have this kind of bypass where all the fabrication steps are done manually. And if one of these walls is not like, is for any reason like some sort of like specific wall. So we see in terms of like some sort of predefined constraints, the system can operate with a high level of automation. But if there are certain circumstances, you will still, like, these companies will use a bypass where they manually assemble these wall elements to do tasks that cannot be done automatically yet. Either it's the material geometry or adding, like, for example, an extra element that they just do not have like the capacities yet to place them. For example, downspanned beam, for example, one of the reasons why you can't place it with the robot is it's bloody heavy. So, and that is a reason, that's a simple reason that you cannot place it with the robot. And but then for like 10% of the walls or 5% of the walls means that they're going to be run through a bypass that's done completely manually. So just running through, so we have like this production sequence that's more like the mainstream that's fully automated. It's going to be fed by the storage that's coming from the sides. And then you have this bypass that's running like completely manually for special elements. So, and then this is like how one of these elements looks like once they're finished. They're going to be loaded in the truck, brought on site, assembled, and that way how they build their houses. Looking at a more project and not product-oriented company, so it's also like it's carpentry. Their name is Meyer. They're also like in South Germany, and they are like a fabricator of like just 20 to 25 one-family houses, as you can see. So like they are. So what is it like? 800 to 25. So it's like 16 times less one-family housing that they produce, but they have much more bigger scale projects that they're working on. And so since they're working like for an architect or like a different contractor, they have to have a higher level of flexibility. So they are project oriented, and whenever the project changes, they have to change maybe the way of fabrication, even if it's just like in a slight way. And this results in a like different kind of machine setup. So they also have like this joinery machine that does like these kind of beams. Again, what is like one of the most important like differences that you could say is that all these assembly stations for the wall panels, they are stationary. Yeah? So while Vincenka was showing a fabrication line where like more like, yeah, as you have seen like in traditional car industry, where the element like runs through each station to get its additional component, to receive its additional component. Here, these stations are fixed, and actually this CNC bridge that does the automated fabrication process is mobile. So it can run on this rail, and after human labor, it's also like more skilled labor because they execute and they decide which fabrication step when to make. It's not run by the machine. They're going to place, for example, for this layer for the cover, these linear components, and then like the machine is going to run over this element and cut them. So there you see, for example, like this assembly procedure. And what you also can see, these are like the it's also like digital nowadays. So they have all these iPads in these covers so that they can drop in and they won't break. And then they have all this information to produce these elements. So while this high level of automation, like the machine was making like almost every decision, and human labor was just giving like some additional steps. Here, like the main decision how the production workflow is run is still done by the workers that are working in this institution. It also results, so since we have seen like this butterfly table that does not work that well, so they went like to a different company where you actually like can flip these elements on the spot. So they have this kind of scissor that then runs and flips this element like on the spot without needing like an extra element. So it's going to be placed more or less exactly where it was before, and the counterpart is going to be machined by this CNC bridge as well. They also have like an interesting handover because like they then will also want fabrication of the finishing, like windows. What we've seen at Vincenta is also going to be something what they want to do vertically. So the final step is also like a vertical and human labor driven finishing approach. For this, they have like for these bays, like just these, they call it like the company that does this technology is called Technowood. They're from Switzerland. They're so really, really innovative. And they have like, while they have on the one hand, they have these integrated scissors, but they also have like this automated handover technology that enables like bring you like one element from one bay to the other. So this is actually like how it looks like in a similar diagram. So we have here this joinery machine. Here we have like this assembly table with the CNC bridge and a vacuum gripper that can help you like to lift heavy elements. There we have this handover that we've seen with this TVY section that I showed, like another framing station and the vertical finishing station. So you have like all these, for example, like 5 wall elements and the workers assembled in here. The machine actually does like, I think exclusively cutting sequences. So just do exact cutting, all the assemble sequence, all the assembly is going to be done by human labor. So they're going to be fed by here the joinery machine and the storage. And then they are like handed over like to like another bay, and then or like here in this specific area for the vertical assembly of doors, windows, etc., and the finishing and so on. So these are like basically like good like companies to like understand and show the difference between product and project-oriented fabrication systems. This also results in the way, like in the level of automation. So for like the influencing factors for like product based companies have the tendency for a high level of automation as project based companies. You also have seen like the subtractive or additive fabrication step, that the subtractive fabrication steps are highly automated in both ways, and additive or assembly steps are done like still with a lot of more human labor involved. Obviously, it also matters like when the machine was installed. You know, so also like setup that's run that's run in without any change like since 20 years. It's going to have like a different level of automation as nowadays. So that also shows us the trend, and the tendency is to full automation in many ways. And obviously it also matters, and I think it's interesting for us to understand that automation, like when a car company tries to set up a new model, like BMW does the new i3, they will have like a budget of billions of dollars to set up the new fabrication sequence because they're going to produce 5 million of these cars. So since like timber structure, like companies are usually like small companies, especially compared to what we see in, for example, car industry, like the investment for like a new machine setup is like quite huge for any company that's trying to automate processes. And like the bigger the company, it's easier, the easier it is for them like to take the step to do a new automation process. So concluding, that means for like this part, this bunch, these guys, the product-based production setup is fabrication lines. It has like a high level of automation with even the aim for full automation. It has a tendency to standardize elements, and is like working highly efficient in production, and it is adaptive, but it has a little bit lack of flexibility. The project-based companies have like more stationary fabrication islands where you move the where like an element is like not moved all the time, right? It's just like it stays there like for a certain time. It's going to be a fabrication step is executed, and it might move, but it's not like in this continuous movement as you see it in these companies that have like a high to full automation. So what you also see is like a tendency to hire skilled labor. The people that, because they make decisions, they understand like in general the tasks that they actually do, like request like to be better skilled. So they have a little bit of a lower efficiency in the production, but they have a high flexibility for different projects, what is really important for them, because every year they will have to compete to get a new contract from a new architect or engineering or other company to hire them to produce their building parts and their building elements. Also, they have the tendency to work like on the bigger projects. So aside like from Catera, but for example, or like other huge companies, like all these companies that we see on top, most of them, they are like produce one family houses. So they produce like a relatively similar building 1,000 times a year, while they these other companies have like 20 contracts per year and have to have like a better balance, or in regards to flexibility. Just like a quick recap, like also Bluma Lehmann is because they are interesting for us on both sides, because if you know them, you usually know them because of all these extraordinary projects they're like involved in. And they have obviously like super interesting machines set up, like this huge techno wood CNC machining system that enables them to produce these complex elements. But that's actually not their main business. That's the business we might know them for. But if you look at the main business that they're having, like most of them, what they build are housing modules. Yeah, so like this is like a huge part and a huge chunk of what they actually do that make their money with. It's not these extraordinary elements. It is like mass fabrication. And also another thing that they produce, like aside from these building modules, is like silos, and they have their own, or they're like part of them. That's by these two names. Like the Bluma family is a sawmill. So they have like what makes them interesting in many ways. First of all, like they work on all levels, from the fabrication of just like the raw components to the finishing of super complex elements. Also, the main business here in the middle is not what we actually know them for. Yeah, but it shows us that we rely on extraordinary project as a company that has to pay like every month their employees is going to be it's going to be a difficult task. So every company has some sort of like, obviously it's easier to produce standardized components, and being innovative is always like a challenge. So what brings us to like Catera and their vision, that actually like on the one hand shows all these high level of automation and fabrication setups that are super modern, and where they investigate like in all levels, from CLT manufacturing to the construction and the planning and of housing. They actually like produce these, what we would say, most of these already like built buildings look like quite standard and quite rigid. And if you have seen like Hannah's lecture yesterday, so there's a certain like repetition that we can see in all these fabrication sequences and elements, and in the building that results in it. And so this is on the one hand having like a huge or like showing this versatile and automated processes, still resulting in this kind of building strategy, like in terms of still having like an on-site assembly that looks like quite standard, and that also like even says, like that's from their website, that they try to minimize the number of unique parts, that they try to maximize part repetition, that they try to increase factory completion, and they try to minimize field connections. So, and if you look what you are doing and also like what we are doing, that's not exactly like that kind of direction we are going in. Now we try to find some higher degree of freedom, and this is this seems to be like a little bit more of our vision, and also like of what you are going to do. And it's like interesting to see that these companies are like at least the way they present them are going like in a slightly different direction. So quick, because we're running also like, I think we will run late. So let's just like talk a little bit about the trends that we have. 3 more minutes or something, like what is like also upcoming. So what we see, if we look what's like now, we've seen like what is state of the art, what's upcoming, and what's somehow next. We still see a lot of development in automation and the idea of actually like even excluding human labor completely from the prefabrication process. We see a lot of development in communication technology and material development. So this, for example, like is the proposal by Robotic, where like actually no human labor is placed anymore, and where the robot executes all the tasks that we have seen so far in the prefabrication from Vincenka. Like even what they are showing now is like closely what we've seen automated already at Vincenka, but they claim that's what they call this this study that they make. They call it what was it, zero labor. So, and the idea having like a human-free fabrication site the same way Tesla tried a couple of years ago. Another thing that we see is like communication. So we see like augmented reality technology that informs us on-site and off-site about ongoing fabrication sequences, safety systems, computer vision that's going to help us to collaboratively work with robotic systems, and communication technology that connects not just all the machines, but also maybe different fabrication setups in different locations, and even like different providers like the of technology. So it's not just like the customer with the manufacturer, but also the manufacturer with the manufacturer of the machine itself. So the company Tapio that's actually like advocating this trend and working in this is a daughter of Homag Meinman, the provider of the machinery technology that we've seen in Vincenka. And so they have like this concept of connection of all these different machines on different levels, like from the saw blade to the neighbor company that actually then sees, okay, if this machine is jammed, like another company could like take on this fabrication stuff and so on. So using communication in like on every level, in every detail for optimizing fabrication sequences. And last but not least, we see like a lot of is happening like in material development. So we've seen here in this presentation also like the standard developments in CLT fabrication. And there are a lot is done like in material technology, like either it's like these chipboards that are placed on top, if it's like a beach a CLT that's manufactured, if it's like hybrid materials, also, or if it's about research that's done, like for example, by my colleagues at MIT at the moment, where they have like, what happens if we take away a certain amount of material? Can we still achieve like the same bending stiffness, the same usability of the system, and that way optimize the material usage? And with this, I'm at my last slide and want to break down like all that you've seen. And it was like, I think it was a lot of information for just half an hour. If we break it down, what we think what is important somehow for our machines, so that what was the first graphic and what is our fabrication setup being part of an existing setup that you see in nowadays companies, that we have like 4 key elements to think about. And one is adaptability. Adaptability is in this case meant to be the adapt to different challenges and constraints and requests within one building system. For example, a lightweight system or a solid system. Flexibility in this case means that you can exceed the building system, meaning that you can use the same fabrication setup that you use for a lightweight system, that you can use it for solid system. The third thing is mobility, what enables us to work like in different fabrication setups, install them somewhere temporarily, and that way like have a short integration of mobile transportation systems in the fabrication setup to extend the capacity of the carpentry that's actually working on a specific project. Then we move it again and it can move somewhere else, even on construction site, and enable on construction site on-site prefabrication, and that way exceed what is the standard transportation constraints. So take some of the fabrication steps that are usually done off-site, on-site. And last but not least, collaboration. Collaboration, we have seen also what Tapio was like showing. It is like the communication and the collaboration, not just between machines, but also between human labor and machines, because we think that using like just having a full full level of automation, like what the Zero Lab claims somehow, or like is trying to address. We think like the integration of human labor, of skilled human labor in the fabrication process is something to go into and not to go away from. And that's also like where we think that trends and the tendencies that we see might not go in the direction we think is the good one. And with this one last sentence, I thank you for your attention, and I'm open for questions. Okay. If you can, I mean, I can see, but maybe you can read it because you can see both. You're more familiar with that. Huh. Yeah. So, of mass production companies to capitalize on it, since they are already successful automation, is it market demand issues? So the question is, where do you? I mean, my question would, what do you think? Like the question actually, like that's not an answer. It's so, but it's like a first important question is, what does it mean? Like, so for automation, where did it lead to? It didn't lead like to more flexibility, no? So we do not build much more flexible as we did like years ago, no? Like customization is something is like is color, is like a certain like proportion that you cannot change, but it is not like a higher degree of freedom. It's not a higher degree of flexibility. And I think so. I do not know if it's like architects and engineers being lazy, but I think that that if we are also users of technology, and that's actually also one of the reasons why I was giving this lecture, like showing technology, because we are sometimes the guys that invent new technologies nowadays to fulfill our own like architectural visions. And I think so that's going to be a little bit of ping pong at the end. So if we have new machines that are accessible, that's, I mean, we do not develop robots. No, we just develop a specific demand for the usage of industrial robots that was not requested like 10 years ago. So we change. I think so. I think it is a part. It's a design, like in the first quick way. It's not like about architects and engineers being lazy, but I will also say like how many do know about like the what we actually can do. So there's a balance of what is going to be designed by what you know, what you can do, and being informed about the capacities and capabilities of the machining and what fabricators actually can do is going to result hopefully also like a new concept of architecture. Global warming, the disappearance of wood supply sources. Do you think timber construction will still be preferred and top choice for future construction? I'm sorry, I'm already reading the question. I should read it out loud, not just for myself.
Yeah.
Okay. Yeah. So, given all the recent bushfires around the world and global warming and the disappearance of wood supply sources, do you think timber construction will still be a preferred and top choice for future construction, or there will be a change in structural construction methods? So first of all, I think yes, and like also that's a personal opinion that's based on some facts, but we're talking like a little bit what I think somehow is like what would be the alternative like to timber construction? Yeah, so would it be like working with more concrete and more steel? So these are also like just by discussing like what would be the alternative. Timber is a regrowing resource, and obviously that does not mean just chop off all trees that are there and wait for them to regrow. It also like means that we have to have a sustainable management of forestation. But it also means that regrowing resources, also like bamboo. I was working previously, like when I was working in Singapore, I was working with bamboo, for example. It's extraordinarily fast in how it's growing, and can also be like be treated in a similar way as engineered timber. Like you have like all these small elements. So natural grown resources being the important construction material, and even a more construction material. It's, I think, that what we're going to see, at least for the next decade. Yeah. So sense of buildings is not low. Okay. Honey and other, as I realized the cost of this kind of buildings is not low. I wanted to know about the lifetime of these buildings, and I wanted to know, are they worth it? I mean, one somehow is going to influence the other. No, like, I mean, if we do not have like a certain sustainability in the way we construct and build our buildings, then probably not. I think there's also a trend, like we talk a lot about the flexibility of buildings because the time of how we use them has dropped. No, like I think certain buildings could stay longer as we let them be, because we changed the use, and we have somehow fabrication has become so like just building something new has become like an efficient way, so that we tend to, like in many ways, to throw things away instead of like reusing them. So and like I think a lot of buildings that are going to be demolished today like would not necessarily have to be demolished. And we also see their trends and tendencies in researches to reclaim the building material that was used. So life cycle is not necessarily equal to like how long the building stands, but we also, I think we will see more strategies of recover existing construction material that was demolished and reintegrated in production cycles. And I think one of the reasons we do not see it at the moment is the same, is also just because it is expensive, and in the moment it's not worth it. But I'm also honestly thinking that we are facing like climate change issues on a global scale. So we will have to find new strategies to work with renewable resources, and also to reintegrate and reuse resources that were used before. You're welcome.
Okay, with that, maybe let's call it a break. We're half an hour late, but I think we should still do a break. But maybe let's keep it at 20 minutes this time. That's okay for. If it's not okay for anyone, then please just text us. We'll accommodate for that. Thanks, Felix, for your extensive lecture, and yeah, we're all excited to see what's going to happen in timber construction, I guess, in the next years. So yeah, I guess let's take a break, and let's see you all back in session 2 in 20 minutes.
Great.
Excellent. Bye.
Ciao.
Thank you.